Ina mana ina reo rarakitirama tēnā koutou katoa, ko te tumu whakarai topua te whare wananga o tākou, ko Helen Nicholson toku ingoa, nō reira tēnā koutou katoa. Kia ora, my name's Helen Nicholson and I'm the Acting Vice-Chancellor at the University of Otago, and it's my great pleasure to welcome you all to this inaugural Professorial lecture to mark the promotion of Wayne Stephenson to Professor. I'd like to give a warm welcome to you all, but particularly to Wayne's family and friends who are with us in person and online. I'd like to give a special welcome to Wayne's partner, Karen, and their 4 sons, Michael, Connor, Liam and James. And I've also learnt today that Wayne's best man's also here too. So welcome, Kevin. Inaugural professorial lectures are a great opportunity to learn more about our talented researchers and to showcase the excellent research that occurs across the university. And as many of you know, promotion to professor at Otago is not something that's easily achieved. We require our academics to show outstanding competence and leadership in teaching, research and service, and Wayne has demonstrated all of these. As you'll shortly hear, Wayne is a geographer with research and teaching interests in coastal geomorphology. His research is focused on how rock coasts respond to tectonics and climate change. Wayne is also an excellent teacher and a strong contributor to the university, and I've had the pleasure of working with Wayne on the board of graduate studies for a while and can attest to his dedication and expertise in his role as Associate Dean Postgraduate. So congratulations, Wayne, on your deserved promotion, and I'm very much looking forward to your lecture. And I'm now going to hand over to Professor Etienne Nell to provide a formal introduction to Professor Stephenson. Nō reira, tēnā koutou, tēnā tātou katoa.
Thank you. Kia ora koutou. It's an honour and a privilege this evening to introduce you to Professor Wayne Stephenson as the School of Geography's most recently promoted professor. Well done, Wayne. I would like to extend a warm welcome this evening to all of you who are joining us here tonight, either in person or through live streaming, but most especially to Wayne's family and friends who are here with us tonight. This evening's event is a key milestone in Wayne's career. It's a celebration of what he's achieved, but also a celebration of his success as an academic. It's my task and pleasure to provide a brief overview of his many achievements across his career, which have led up to this event tonight and to his promotion. As I'm sure Wayne will share with us shortly, he was born in Dunedin, but has very strong roots in South Otago. His tertiary education was all undertaken at the University of Canterbury, where he had the good fortune to be mentored by Professor Bob Kirk, who supervised Wayne's PhD, but whom I am told played a formative role when Wayne was in the first year of his studies. Apparently on a memorable field trip, he encouraged Wayne to blend his interests in both physical geography and scuba diving. Now, all of those come together quite nicely, I'm sure, in what we'll hear about tonight. I'm told that the result of this interaction was many enjoyable trips to look at both the geography and to do scuba diving, particularly at Kaikoura. Now, Kaikoura is a place we'll hear a lot about tonight. It's been quite key not only in Wayne's PhD work, but also the extremely significant research work he's undertaken there, most particularly not only in his PhD, but more recently in the 2016 earthquake in and around Kaikoura. A major event which led to a dramatic uplift of the seabed, an event which Wayne has studied in depth and one which has certainly strengthened his academic standing as a scholar. Wayne is a geographer with specialist expertise in coastal geomorphology, and more specifically how rock coasts respond to tectonics and climate change, including the investigation of complex interactions between processes of coastal erosion and sea level rise. His PhD examined the evolution of shore platforms in Kaikoura. Before joining us at Otago, Wayne was a senior lecturer at the University of Melbourne, and across his career he has undertaken work, research and research collaborations in the Maldives, Mexico, the UK, USA, China and Australia. Through his research work, he has led investigations into sea level rise, marine terraces, and coastal erosion. His work has enabled direct collaboration with iwi, regional councils, and numerous coastal communities. The applied significance of his work is borne out through an impressive range of technical reports and advice rendered to numerous authorities, including the Port of Lyttelton, Port Otago, the UK government, the Murray-Darling Basin Authority, and numerous coastal communities across Australasia. These applied contributions are matched with his significant research output. To date, he has 74 research articles and chapters to his name, and an authored book entitled Rock Coast Geomorphology. Many of his published articles are in well-respected international journals, such as Earth Surface Processes, Nature Communications, Geomorphology, and Coastal Management. As Wayne's career has strengthened, he has been able to support a growing number of postgraduate students, some of whom are here tonight and some of whom are watching over the live stream. He has supervised 48 postgraduate students to date, including 13 PhDs. In terms of external service, Wayne serves on the boards of 2 international journals and has been the editor of 2 other journals, namely Geographical Research and the Journal of Maps. In addition to his highly successful publishing and research career, Wayne is a well-liked and well-respected figure on our campus and in our school, and in the Division of Humanities he currently plays a critical role as the Associate Dean Graduate Studies. In geography, he has played key roles in on our Teaching and Learning Committee and through his coordination of our key and very popular first-year paper in Environment and Society. Having outlined Wayne's impressive and very successful academic career, it would be remiss not to also mention Wayne's various other interests. Most prominent amongst these is ultramarathon running. 4 days ago, he participated in the 56-kilometre long Three Peaks Marathon, which I'm told has a height variation of several thousand metres as it progresses around the hills of Dunedin. Well done, Wayne, on completing that. So with those words of introduction, I would like to warmly congratulate Wayne on his well-deserved promotion and invite him to now address us. Thank you, Wayne.
Etienne, can I have the green folder back?
I won't do that one.
Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko ingarangi, ko porohia, te whakapapa mai. Ko autatahi, te whenua tupu, ko autapoti, te kaianga. He Pākehā aho, ko Wanda Stephenson, toko whea. Ko William Stephenson, toko matua. Ko Wayne Stephenson, tako ingoa. Kia ora, everybody. I can't look at that yellow slide anymore, I'm sorry. Thank you very much, everybody, for coming. It's wonderful to see so many people. Helen, Etienne, thank you so much for those wonderful words of introduction. I feel like everything's been said and perhaps we should just go to the staff club now. But I guess in some ways I'm very nervous, but I'm also obviously very excited to be able to share with you the work that I've done as a geographer over the years. So I had to prepare the title for this talk some weeks ago, and I realised in the preparation of my talk I'm now going to overpromise and underdeliver. The elements of this coastal erosion will come through. I'm afraid the sea level rise part of this isn't quite as strong as I originally anticipated. I am certainly going to talk about the earthquake in Kaikoura, but as a geographer, I'm very proud to be a geographer. But I like to do geomorphology, and that's the specialism that I'm most interested in. So the play on words here is about between the rocks and a hard place. So much of my research is on the rocks, and I'm going to highlight a couple of hard things about being a researcher and doing research. So I'm going to start by talking about why I think rock coasts are important and worthy of study. In the tradition of an IPL, of course, I'll tell you a little bit of the backstory about how I got here. I've spent a lot of time over the last few weeks reflecting on how I got here, and there's a lot of elements to that story. And I've kind of got to that stage in my career where I can certainly divide my research into 2 components. things I did before the Kaikoura earthquake and things that I've done since. And then, of course, I'll finish with some thanks and some acknowledgements of some of the key people that helped me get here tonight. So I'm going to start with a hard place. And the hard place is the passing of my PhD supervisor, Bob Kirk, on the 4th of March. Bob was a really important part of my story, and that hopefully will come through tonight. The part of the problem here, and the reason I'm starting to get emotional, was that this morning was the memorial service for Bob, the celebration of his life in Dunedin. It was held in Christchurch. And I was torn between asking to postpone this evening and attend the ceremony for Bob. I didn't trust Air New Zealand to get me back into Dunedin on time, and I could also hear Bob saying, "Do the IPL, you silly bugger." And I'm quite certain that is the sentiment that Bob would have had if I had the opportunity to ask him. So you'll see tonight, Bob will come through this story quite a lot. And so I'd like to dedicate tonight in this IPL to the memory of Bob. Rock Coast. I love Rock Coast. They're spectacular. They're fantastic things. In some ways, they're very simple. They're often typically just a cliff, and a cliff's a cliff. But if we travel around the world and we look at rocky coasts, we'll see an enormous amount of variability and really wonderful landscapes. And I guess as a geographer and a geomorphologist, I'm intrigued and I love to look at these things. I could show you lots of slides of Rock Coast, but I'm not going to take up all my time with pretty pictures. Rock coasts are often thought of as slow to change and resistant to climate change, for example, resistant to sea level rise. But we know actually that they can be dynamic and they can change very quickly. So this is the Great Ocean Road. These are the 12 apostles on the Great Ocean Road in Victoria, Australia. And you can see this particular sea stack in 2005 fell over. And a few years later, the arch at Lockhart Gorge, just a few kilometres down the road, collapsed. And this led to the mayor of the local shire, the local council, to call for protection works to be built to protect these valuable assets. And in my commentary in the local media on this, I made the point, well, actually this stack fell over on a relatively calm day. Okay, it wasn't particularly energetic. And never mind the point that the collapse of the arch actually created 2 new sea stacks. But that call really sort of underpins the importance of Rock Coast, because of the concern, of course, was that these are a valuable asset. They actually generate income and they generate and provide for the tourist economy. So at the 12 Apostles across the road, there's an elaborate visitor centre. Okay, and so there's an enormous amount of infrastructure built to support the tourism industry, and the attraction is the rocky coast geomorphology, the sea stacks, especially at the 12 Apostles. So Rock Coast, aesthetically pleasing landscapes that have important economic value. So understanding how they evolve and change through time, I think, is worthy of research. They also present hazards as well. So coastal erosion, especially if sea level rise is making this worse, means there's a significant management issues around rock coasts. The hazards that rocky coasts present are not just community-wide, they can also be individual and threaten individual lives. And it's not unheard of for people to have been killed by rock falls beneath sea cliffs. So just note the little corner of this particular piece. I've been photographing this section of coast as again at the 12 Apostles, waiting for this whole piece to fall off. The last time I was there, a little corner of it had fallen off, and that had resulted in a sign warning people about rockfall. And to be careful of this threat when you like this one, you're going to love the next one, because individuals can be killed by rockfall. But it doesn't matter how good your signage is. Some people will accept and take the risk and sit at the base of the cliff. So coastal hazards as well. Now, it used to be the case that, and I used to take great pride in this, we could claim that about 80% of the world's coastline had a cliff or was rocky. And that was all right until the satellite data arrived, and some analysis of the satellite imagery showed that actually it's only probably about 50%. So half the world's coastline has a rocky morphology or a rocky shape. So these are a significant coastal landform. The other landform that we often see on rock coasts isn't just the sea cliff, but also this feature, a shore platform. So there's level, flat bedrock surface. They're typically intertidal, so this photo's at low tide. High tide comes up and the surface is covered by the sea, so waves can move across it and help erode the cliff at the back. The key thing is that these are erosional landforms, and so the coastal erosion in my title is covered by everything I talk about tonight. The important thing there is that because they only erode, their trajectory into the future is inland. These are not like beaches or mangroves or coral reefs that can actually respond dynamically to sea level rise and climate change, that can recover after storms. Rock coasts only erode. So in that way, they're kind of actually more vulnerable to climate change and sea level rise than the landforms that we traditionally think of, such as beaches, coral reefs, or mangroves. But my interest has been in trying to understand how this landform evolves and changes through time. And of course, I'm interested in what the future of these kinds of coastal landscapes might be as sea levels rise and as climates change. And rocky, again, shore platforms are spectacular landforms. They're widespread around the globe. They come in a variety of variations, although the simple form of a cliff and a platform is consistent. They have quite a bit of variability in their width, their elevation, for example. So this is one of the more spectacular platforms I get to visit. This is in South Wales, on the Glamorgan Heritage Coast. This platform is about 300 metres wide. It's a very large and spectacular landform. Now, the thing that we're interested in is trying to understand how these landforms come to be. So geomorphology is essentially about why do landscapes look the way they do, what are the processes that cause those landscapes to evolve, and what might the future of these landscapes be. And that question about how these landscapes come to be has been with us in the literature for a very, very long time. In fact, one of the world's most famous coastal geomorphologists, none other than Charles Darwin, wrote about rock coasts. He couldn't understand how the sea could erode such resistant rock as basalts that he observed on St. Helena Island in the Atlantic Ocean. And he posed the question, how has all that hard basaltic rock been eroded or swept away by the sea? And that basic question has been with us ever since. We continue to be challenged by this question. New Zealand's had a role in this. This is the Mill Island. We know it as the Old Hat because it looks like a hat in the Bay of Islands. And an early geological survey by Dana speculated about the role of waves eroding the bedrock at some level of greatest wear, somewhere around the mid-tide level. Later, a New Zealand geologist, Bartram, reappraised the Old Hat and said, no, it's not about wave erosion. Actually, the waves are very weak here. It's really about the weathering of the rock, the subaerial processes, wetting and drying, salt weathering, that weaken the rock to the point that you only need very weak waves to remove the weathered debris. And so that's set up a debate that's been in the literature for well over 100 years now, waves versus weathering. What is the process responsible for these landforms? And it's continued to be an issue and an argument amongst geomorphologists. Even as recently, Dave Kennedy and Mark Dixon have reappraised the Old Hat, trying to get to the answer of this question. So really that's what I've been interested through my career, is trying to understand the processes responsible for eroding rock coasts. It might seem simple that it's either waves or weathering, but when you want to start making predictions about the future of these kinds of coastlines, you really need to know what is the relative role of those processes when you're trying to build models to make predictions. So, Darwin's hand-drawn diagram eventually gets into his book on the geology of South America, as around this question of the sea, eroding sea cliffs. That basic question is what interests me, but before I get to that and talk about how I've gone about answering that, here's the backstory. This is a little bit about me and where I'm from. And now what I really want to do is acknowledge my grandparents on both sides of my family. Their stories I think are really interesting, and I've always had an enormous respect for my grandparents. I think of them as the war generation. Of course, they're no longer with us. But this photo here's my grandmother, Maria, and my grandfather, Jan. We knew him as John. But this is a photo from about 1946, maybe early 47. Grandfather there is wearing a British Army uniform. He spent 5 years serving for the British Army after World War II. But during World War II, both him and my grandmother were slave labourers in Germany, and had a pretty traumatic time of it. At the end of their service, my grandfather's service, they immigrated here to New Zealand. They came into Wellington on a ship called Hellenic Prince Te Waka. Okay, and here's my grandfather as a carpenter and a handyman working on the Waitaki power scheme in the 50s. Unfortunately, my grandmother's wartime experience left her suffering quite significant mental illness issues. She didn't cope very well with the move to New Zealand. The marriage unfortunately ended, and my grandfather moved on and created a blended family here in Dunedin. He spent most of his life working as a handyman and as a carpenter in Dunedin. On my father's side, Dad's from Kaitangata, and this is a photo that there are actually 4 Stephensons in this photo. I'm very proud of this one. This is the Volunteer Fire Brigade in 61, as we can see. There's my grandfather, Jack Stephenson, his brother, Uncle Joe, his other brother, Uncle Algie, and there's a young Bill or William Stephenson, my father. Okay, and of course they were all coal miners. Okay, and my grandmother's father was a coal miner as well. So there's an irony there, I think, in terms of where I am now, thinking about climate change and sea level rise. Dad's interest in firefighting took us to Christchurch. He joined the Royal New Zealand Air Force. I was born here in Green Island. When I was in 74, we moved to Christchurch. Dad joined the Royal New Zealand Air Force as a fireman, and I grew up in and around Wigram Air Force Base. That meant I went to Hornby High, and I was not in any way an academic student. Somehow, and for reasons I never really understood, in 1986 they put me on the cover of the school magazine. And now some of it, I've included the other image here because I appreciate some people in the audience won't remember the young ones. But I loved the young ones. I thought it was such a cool program. And I was thrilled to be Rick because I liked Rick. I liked his anarchist views of the world. I liked his anti-establishment views, his anti-authority views. And some of you who know me will now understand where my own politic comes from. I wasn't successful at school. In fact, one year, the dean of the 7th form dean, who was the head of geography at Hornby High, said, "Stephenson, you're nobody going nowhere." And well, Mr. Duffy, here we are. Look, I enjoyed sports at school. I played rugby, and I guess ultimately that's where my interest now in running comes from. I was not good at rugby. I spent more time carrying the oranges than I did the rugby ball. But there's some lifelong friendships and relationships here. This is my brother-in-law, Roger. Okay, so we've been brother-in-law now for nearly 29 years. There's me with some long hair, and there's one Kevin Sewell standing in the background. Hey, we've done all right, haven't we? Hornby High, we moved on to University of Canterbury. Kevin and I went to University of Canterbury. And as was said earlier, that's where I first met Bob Kirk and was influenced by and inspired to do physical geography particularly my master's, but then my PhD. And so for my PhD, I returned to Kaikoura. I came to Kaikoura for my PhD. Kevin and I had been going to Kaikoura for years before to go scuba diving. So I went there and to do my PhD. And I was basically interested in this question of waves versus weathering. What are the processes responsible for creating a big, wide shore platform like this? Now, that work that I started was built off work that Bob Kirk had started 20 years before me. And I like this photo. This is Bob from some years ago now. This is a colleague and a friend, John Allen. We did our PhDs together. Look, I think that my joke here is, behind every successful academic, there's a PhD student pushing really hard. Okay. And I'm going to keep that going, I think, when I show you some of the work of more recent work. Bob set up a monitoring program at Kaikoura on the shore platforms, trying to measure the erosion rates. He was interested in the rates and speed of development of these landforms. He started that in 73 and 74. I went there in 93 and reinvigorated the network that he installed. And that network was based around what was then cutting edge technology. Okay, this is a micro erosion meter. It's a very cunning device. If you put 3 bolts in the rock surface, you can, every time you come back and put the instrument on the bolts, you get the exact same position. And this particular instrument at the top here, you can get 3 readings. This one at the bottom, you can get 120 readings from. And so across these profiles on the platform, each of these letters and triangles, we installed these bolt sites, and we would go back regularly and remeasure. And as the surface goes down, we record the elevation of the rock surface through time as the erosion proceeds. This is an instrument that takes 120 readings, as I just said. It meant you had to spend hours collecting data. And Karen is well trained as an MEM operator. She spent an enormous amount of time during my PhD helping me collect those data. Up until 2016, the Kaikoura earthquake, we had, at the height of the monitoring, 54 bolt sites across these 7 profiles. We had over 25,000 individual point measurements of rock surfaces. So we had a very large data set. Out of that, though, lots of papers have followed, and I think this is probably the most important part of the MEM, I refer it to as the MEM, the Micro Erosion Meter Network at Kaikoura, is that we've been able to create a very long record of erosion rates. And so the original work that Bob did was only measuring rates of around 2 years. In fact, other studies typically are of about 2 years. And one of the criticisms has always been that that's a relatively short period of time to measure erosion on a landform that takes thousands of years. So can you really extrapolate the erosion rates? So we've been able to measure those bolt sites after 20, 30, and 43 years in 2016 and extend our certainty or our understanding of those erosion rates, at least to decadal scales. And what we find is that statistically, the 2 years of data is identical to the decadal length. So we've got a little bit more confidence in our ability to extrapolate these data. And I think it's fair to say now Kaikoura is recognised internationally for the length of its record of monitoring erosion on platforms. Now, the platform erosion rates is fine, and you can learn some things from it, but it doesn't get at the heart of that question about the relative roles of waves and weathering. The question I had for my PhD is, do waves erode platforms? And so I took a very geomechanical approach to this, where we essentially went out and measured the waves to calculate the forces that the waves induce on the rock surfaces. We calculated the strength or the resistance of the rock just through some geotechnical techniques. And what we find is we use a very simple relationship where we say erosion will occur when the wave forces exceed the resisting forces of the rock. Okay, that's when we see erosion. While if we quantified resisting force and wave force at Kaikoura, what we discovered is that the forces induced by the waves are nowhere near the resisting force of the rock, orders of magnitude less. Okay, so how could waves be responsible for eroding these shore platforms? The other part of that story, of course, is the weathering, and so we looked at the weathering. We tried to work out how efficient the weathering was, so particularly wetting and drying and salt weathering in this environment. And so here's the same rock from Kaikoura after just 20 cycles of wetting and drying in fresh water, not even salt water. It basically fell apart. And we know from work on the platforms that these surfaces can have up to 400 cycles of wetting and drying per year. And so the argument has been, actually, it's necessary to have the weathering of the surface so the weak waves can remove the debris produced by the weathering. And that's exactly the same story that Bartram proposed, the idea or the theory that Bartram proposed in 1916. So we very much landed in the Bartram camp in the waves versus weathering debate. Now, my interest in waves on shore platforms has continued through time, and in fact more recently we've had work being done on wave transformations on platforms by Rafael Correa Mariani for his PhD. Raf's done an amazing job. He has one of the most detailed data sets on wave transformations across platforms ever collected. And it's a credit to Raf for all the hard work he did. And it's a little, I know it's a cliche, each of these little grey squares is an instrument measuring water level, measuring waves. Raf was cunningly able to use some very cool math to calculate what was happening to the waves, not just at the instruments, but between them as well. And so he's built up this really complex picture of wave hydrodynamics on shore platforms that really has changed the way we understand wave transformations across these surfaces. The colouring is just the dissipation of energy. Hot red is higher energy, lower energy in the blue. But importantly, Raf was able to show not just the cross-shore change in wave energy, which is what people had been focused on, but he was also able to illustrate the along-shore variability as well. That's largely determined by the morphology or the shape of the shore platform. And Raf's pushed me really hard, okay, and but one of the things I like to do is claim that I've got some happy PhD candidates. Raf's gone on to work for the Dunedin City Council and has now just taken up a postdoctoral fellowship at Scripps Institute of Oceanography in San Diego, so he hasn't had to rely on Plan B. Okay, he's doing really well. There was a move to Australia after the PhD work, and lots of things happened in Australia. One of the things I was able to do when I went to Melbourne was pick up a micro-erosion meter network that had been installed in 1979 by Edmund Gill, mostly around Lorne on the Great Ocean Road, along the Otways here. He had done exactly the same thing that Bob had done at Kaikoura, and we were able to find the bolt sites again. I was able to find his instrument, and I actually even managed to find his handwritten notes and original data, so we could recalculate and remeasure almost 95% of the bolts that he installed. And what we found is the erosion rate over 32 years was just slightly less than the erosion rate over 2 years, but still statistically the same. So again, we had confirmation that decadal rates and 2-year rates are the same. So we can extend shorter term erosion rates, at least to the decadal scale. So that was quite useful. That work's been picked up and carried on by Ranji Yuan for his master's thesis and then his PhD. And Ranji's done a fantastic job. He's an absolute machine with the publications. I've reduced the supervisors to et al. Tonight because I put these up to celebrate the efforts of the students, not me or the co-supervisors. Ranji's done lots of work remeasuring the bolt sites regularly. He's also done lots of controlled experiments in the lab with an environment cabinet, controlling temperature and moisture and water, heating and cooling, and has been able to isolate those different subaerial weathering processes out to see how they cause erosion. So Ranji's done a great job. He's now in a lectureship at the University of Melbourne, so another success story. There's a slight shift now. Alongside that work in Australia, I began working in the UK with a colleague, Larissa Naylor, and I'm not sure if Larissa's online at the moment, but hi Larissa if you are. Larissa and I met at a conference many years ago and started talking about erosion of shore platforms and rocky coast, and particularly the use of the micro-erosion meter. And we had doubts about the validity of that method, particularly the scale at which you measure. You measure at a very small scale, but Larissa knew from her PhD work that the platforms that she had been working on don't come apart at the millimetre or the sub-millimetre scale, they come apart at the metre scale. And that's because the site that she worked on, the geology was a series of layered limestone with thin layers of shale in between, tightly jointed. And so when it eroded, it produced big blocks of rock, not small fine grains that I'd been seeing at Kaikoura in Australia. So we started playing around with this idea of geological contingency. That, and this comes out of Jonathan Phillips' theoretical work that says general models for landscape evolution fall down at the local scale because of local factors, and they're contingent on history, processes, and geology. So we started comparing erosion products at Glamorgan with Australia and Kaikoura, and what we found, of course, is that the geology is in control here. It determines the scale at which the erosion occurs. And it's because of the tightly jointed limestone, the joints weather, okay, and they weather quite well, and you can see it when they fall apart. there's actually a pool here, like one of these pools, and the brown colours that you see going down the face of the joint is the weathering down that joint. And a lot of it's done by the biology, but that weathering weakens the joint to the point where the waves suddenly are able to pick up the blocks of rock and move them away. This was interesting because people had been putting micro-erosion meters on the surfaces of these layers of limestone. But we were seeing blocks of rock literally being stripped away in single storm events, entire layers of the limestone. But you still needed the weathering in the joints to enable the waves to do that. So again, we're talking about Bartram's weathering necessary for the erosion by waves of the rock. We spent, and more recent work, Danielle Buchanan's did this for her masters. She did this in a much larger scale and was able to calculate erosion rates and found that the erosion rates were in fact an order of magnitude higher than the micro-erosion meter rates that have been measured here. So there's a question around the validity of micro-erosion meter. 25 years of research, and I'm thinking, maybe I've been doing it wrong for all this time. But there are still really important questions around scale in geomorphology, and particularly in the measurement of erosion on these rocky coasts. Okay, that gets me back to Kaikoura. Okay, so there was a move back to, we came to Dunedin in 2010, and of course the earthquake in 2016. There's always been an interest in the question about the role of tectonics in rock coast evolution. We've known pretty well that there's a role here, but the opportunities to observe the immediate impacts of an earthquake, and particularly co-seismic uplift of the coast, are relatively rare. They're not unheard of. Darwin had an opportunity on the voyage of the Beagle to do that, observed shorelines a few years after an earthquake. But what is rare is to have a site uplifted where you have 43 years of data. And I think that's where I got lucky. I literally won the geomorphology lottery in terms of this earthquake. So we were able to go to Kaikoura and think about these surfaces and what does tectonism, what does uplift during an earthquake do to those processes that we'd been investigating and those rates of erosion that we'd been measuring. We also can now link to another branch of the earth sciences, and that's the paleoseismic work that the geologists do. When you uplift a shore platform out of the tide, like that one, you create marine terraces. And this is a photo from the work of Kelvin Berryman at GNS Science. This is Mahia Peninsula up in the North Island. There's a modern shore platform in the front here, but behind that is a series of terraces, of a staircase of terraces. And each of these surfaces that you can see here, we can date those, we can look at the elevation of them, and this is what the paleoseismic people do. You can calculate the return interval and the magnitude of the earthquakes that created those marine terraces. And these are global, these features. You can find them in lots of places, and lots of people use them to construct paleoseismic records. The thing though is, if the uplift is the right amount, and if the shore platform remains connected to the sea, the shore platform continues to develop. And so the processes of the shore platform widening erodes the newest marine terrace. And eventually what you can do is you can actually remove the last marine terrace from the record. And so if you go to Mahia and you map 4 terraces, how do you know there wasn't a 5th terrace? How do you know that if there's one missing, or maybe 2 missing? So that's one of the problems that we've been able to start investigating through a Marsden-funded project that has allowed us to look at Mahia and Kaikoura as the end members of the story. Mahia is the end of the life of a marine terrace, and Kaikoura is the beginning of a marine terrace. And of course it is because of the 2016 earthquake. It's not that long, it's still relatively fresh in the memory of some people, of course. We know magnitude 7.8 on the 14th of November 2016, significant seismic event for New Zealand. This is where we get to be in one of those hard places, and this is interesting. As a geomorphologist watching the images on TV, I couldn't wait to get to Kaikoura. I just wanted to get up there and see what had happened. But of course, Kaikoura is a community of people who have been traumatised and impacted badly by that earthquake. We know about the damage to State Highway 1, the main trunk line. Just getting to Kaikoura in the early weeks after the earthquake was a major challenge. 2 of my 3 favourite pubs in Kaikoura were destroyed, okay, and of course the impacts on the coastline as well. Now, I made a promise to some people I wouldn't tell very many running stories tonight, so here's my one and only running story. And it really goes to this idea about what it means to be a researcher going into a community traumatised by earthquake. In 2018, I was running the Christchurch Marathon, and it's a short run, I got talking to the woman alongside me. You tend to do that when you're running, it helps the Ks tick away. And we were running through Avonside, which was by that stage just empty lots, grown over with weeds. The houses had been removed. The streets were still sort of paved, but pretty bad shape. And I made the comment, this is a really depressing course to be on for a marathon. And she said, I used to live here. And it turned out she was a teacher, I think at Avonside Girls High. Her house had been destroyed. She'd lost her job. Her husband had lost his job. And she was telling me all this, and I was thinking, oh, this is awful. And then she said to me, what do you do? And I said, wow, I'm interested in earthquakes. I'm studying Kaikoura, and I'm looking at the uplift that was caused by that earthquake, and I'm trying to understand what the future of that coastline might be. And she said to me, that's really interesting. You're so lucky to have had an earthquake. I didn't have anything to say at that point, but the point is, as earth scientists, as geographers, geologists, whatever our discipline is, when we work on disasters and hazards, working with those communities and being in those communities is often quite hard because you are in amongst people traumatised by those events. So if there's any message in here tonight, and I know this won't be news to the folk I'm talking about, but just being mindful of the communities you're working in. At Kaikoura, the whole peninsula came up a metre. Further north it was up to 6 metres, further south it was actually subsidence, but the peninsula itself popped up a metre. And that means those profiles with our micro-erosion meter bolt sites on it were now, many of those sites were now supratidal. They were above the tide. They were no longer shore platforms. They were now brand new marine terraces. And the profiles that you see, some of them were made much longer. Seafloor came up from being subtidal to being intertidal. And so the landscape changed dramatically. The holdfasts of the Davilia here and the white, that was all subtidal before the earthquake, just to illustrate the amount of uplift. And here's the beginning of a brand new marine terrace. So here's a site just a few weeks after the Kaikoura earthquake. This is a gravel beach. This is where high tide used to be before the earthquake. This is the high tide on the day I took the photo. This was intertidal shore platform. It's now a brand new marine terrace. And over time, we've had the opportunity to observe and record the accumulation of sediment and the development of this marine terrace. So the rocks began to weather, the waves, still some waves were able to wash in seaweed and driftwood. The plants moved in, and now remember that used to be intertidal. It's now a piece of land with grass growing on it, and it is what we recognise as a marine terrace. The other thing we were able to do, of course, was continue measuring the bolt sites, these micro-erosion meter bolt sites. So this is one of these sites just a few weeks after the earthquake in December 2016, and here it is in December 2023. Now the important point here is that you can see the accumulation of the weathered debris on the surface. The surface continued to weather. Okay, the mudstone kind of contracted and cracked and broke down and produced all these fragments. The important point is there are no waves anymore. So that weathered debris is not being washed away as Bartram described it should be. So again, another little piece of evidence in support of Bartram's view of weathering and the removal of debris by weak waves. When you stop the waves, the debris accumulates because the weathering processes go on. They're not as efficient or as fast. The wetting and drying cycles are much reduced, but the rock surface is still weathering. Now, finally I've got some data to show you. It's been a long time coming. If we've been able to measure these bolt sites quarterly since 2016, subject to COVID restrictions. There's a few gaps, but if we actually look at some data, each of these panels is one of the profiles, or the 7 profiles, and each of the lines is one of the bolt sites. And we've got here elevation of the bolt site through time from 2016 at the start up to December 2023. And you can see the general story is the surface continuing to lower as we might expect. The grey envelopes are actually the pre-earthquake rates. Okay, so this is the range of rates we had on the bolt site before the earthquake. So if nothing had changed, we would expect these lines to be inside the grey envelopes. But as you can see, many of them are not. They're actually lowering much faster. Some of them are still within those envelopes, but they've moved their positions. Some are towards the bottom. But actually, some of the sites have actually, the surface elevation has increased. And that's the accumulation of that weathered debris that's not being removed on these supratidal bolt sites that are on the new marine terrace. And in fact, they dropped out of the record pretty quickly because basically the bolt site became buried. We could no longer find it under the debris that was accumulating, the sediment that was accumulating. We've lost a few bolt sites. The bolts where the erosion rates have been quite high have simply dropped out. But overall, our erosion rate data pre-earthquake in the grey here and post-earthquake in the red here is significantly different. Okay, the rates are really different from before the earthquake compared to after the earthquake. That might not seem as a surprise, but it is demonstrating the impact of the earthquake on these erosion rates. Again, a busy table. What we've got here is each of the 7 profiles. We've averaged all the bolt sites together to come up with a profile average. And then at the bottom, we've got the average of the 7 profiles. These first 2 numbers are the erosion rates before the earthquake. And these numbers are the erosion rates after the earthquake on the anniversary of the earthquake. And what you see, of course, is that the erosion rates have more than doubled since the earthquake. Why does that matter? Well, if you think about that metre of uplift since the earthquake, the platforms have come up a metre. At those rates of erosion of 2 to 2.5 millimetres per year, you only need about 450 years to erode that uplifted surface. It's a very simple linear calculation, I know, but I haven't got time to go into the details. But the point is, if it only takes 450 years to remove that marine terrace, that new marine terrace, it isn't in the landscape for very long. And it turns out the return interval of earthquakes at Kaikoura is around 700 years. So it's quite conceivable that the new marine terrace we observe today will be gone from the landscape before the next earthquake, which means the geomorphic record and the geological record of the 2016 earthquake could well disappear. And so that's the message that we're sort of promoting at the moment. The geologists kind of know that there's a chance that they might not have all their marine terraces, but actually now having been able to put some numbers on the rates of and how quickly these things erode or disappear has been quite useful. And so our future work is really around trying to better refine that model to predict how long marine terraces last in the landscape. Part of that story isn't just based on the measurements that I've made with the MEM, it's also based around the work that some of the PhD candidates in the project have done as well. So here's Sophie Horton. Sophie was asked to look at the changing in processes at Kaikoura, and she worked at Kaikoura and Mahia. She's done some great work examining how wave transformations have changed over the platforms, and importantly, how the weathering processes have changed on the platforms as well. So Sophie developed a really cool little model for calculating the number of wetting and drying cycles, pre-earthquake and post-earthquake. And it's reliant really on the change in inundation by the tide, the weather conditions, but Sophie could show us, or did show us, that pre-earthquake those platforms could have anything up to 400 cycles per year. Post-earthquake, they're down to 20 or 30. So the process regime has changed dramatically as a result of that earthquake. And so we've been able to better understand those things, and so that better informs the models that we're now using to predict the longevity of marine terraces. Happy PhD candidate. I don't know if you're watching, Sophie, but this is your punishment for photobombing my photo. Sophie's now at University of Canterbury in a lectureship there. She's just moved to Canterbury after a teaching position at Oxford University. I was trying to take a photo of Joe Katola in the back there. And Joe Katola was another PhD candidate on our project. Joe Katola was interested in understanding those erosion rates that we've been measuring with the microerosion meter, but mindful of the problems that we knew about in the microerosion meter data, and so applied a new technique, or a more recent up-to-date technique, to try and measure the erosion rates. So Joe Katola spent hours hunched over bolt sites taking thousands and thousands of photos, and those photos analysed with a technique called structure for motion photogrammetry. We basically create a digital elevation model of the surface from all the photographs. We can repeat that, compare the differences between those models, and calculate the erosion rate over a much larger area than just the microerosion meter. And so Joe Katola did that at a much larger scale than the MEM. The targets just help control the photographs. And Joe Katola could show us that the erosion rates scale. That is, the bigger the scale that you measure out, the bigger the erosion rates. So that's been quite an important outcome. And we see here the statistical differences between erosion rates depending on the scale that you've measured them at. So in blue is the microerosion meter. The micro scale is using the photogrammetry on the bolt site. And then the mesoscale is using it over about a square metre. And the photogrammetry reveals the scale of the erosion products, the size of the bits that are coming off the surface, and we've been able to see that in great detail as well. And again, these kind of data will go into the numerical models that we use to predict the future of these landforms. Happy PhD candidates. Joe Katola is now a senior coastal scientist for the Auckland Council. Just a shout out, this is Brendan Hall, a technician from the University of Auckland, who helped us a lot of the field work. Okay, I want to finish with some thank yous. And this is the Marsden team. I've had the privilege of working with some great people. The Marsden project, I think, is perhaps one of the longest running Marsdens on record. We've had multiple extensions, COVID of course, but that's been, in a way, that's been a bit of a silver lining, because it's really given us time to sit and think about what we're doing and really look in depth at our data. So Kevin Norton, Victoria University, Martin Hurst at Glasgow University, Hiro Matsumoto, he's our numerical modeller, he's the one doing all the really hard work now that we've got all the data in, and Nicola Litchfield, GNS Science. Nicola's our seismologist, our seismic person who keeps the geomorphology real. And this is Mark Dixon, Auckland University, my co-chief investigator. Mark and I have had some great time over the last few years arguing about waves and weathering and rates of erosion on shore platforms. My biggest thanks has to go to Karen. Sorry. Here we are in 94, I think, maybe 94, I can't remember exactly. Karen helping with my fieldwork. Karen spent hours and hours and hours at Kaikoura measuring all those bolt sites with me. Here we are last year, effectively the 30th anniversary of working at Kaikoura, and I'm not going to make the obvious joke about Karen being my rock, okay? Because clearly the rocks at Kaikoura are not as supportive, as stable as Karen has been for the last almost 29 years. Thank you, Karen. I'm going to finish where I started, and that's in memory of Bob. Bob was a DVC, a head of school. He was an awesome scientist. But for me, and to many people that Bob taught over the years, he was a teacher, he was a supervisor, colleague, collaborator, mentor, and of course, friend. This is Bob doing fieldwork. This is Bob doing geomorphology. He happens to be on the phone talking to the University of Canterbury as the DVC manager. So I like this. Here he is managing the University of Canterbury from a shore platform at Kaikoura. This quote is actually from the acknowledgements of my PhD I wrote in 1997. And one of the things about Bob was he was very keen to see people be given opportunity. And that was mentioned today in his memorial service as one of the hallmarks of his time with us. I've always been grateful to Bob for the opportunity he gave me, and I will always be grateful. Thank you.
koutou, ko Jessica Palmer toko ingoa ko te mana kura o Te Kite Aranui. It's my great pleasure as the Pro-Vice-Chancellor of the division in which Wayne works, Division of Humanities, to offer a vote of thanks to Wayne. And I think you'd probably all agree that in this lecture we have seen the display of scholarship at work, and that it looks like observing things, testing hypotheses, being prepared to make space for factors you hadn't initially expected, and then following a new line of research. And of course, you blessed us with, or privileged us with, some data, which, and I'm smiling because we don't get that in all of our humanities lectures, so it was lovely. Thank you, Wayne. I think too, I want to acknowledge and thank you that you have made a point of supporting PhD students in your research, and that's clearly important to you. In your IPL, you showed that clearly, and it's wonderful to see how many of them have gone on to become researchers in their own rights, and that's a really important part of what we do as researchers here. And finally, that you do it with colleagues. Colleagues are so obviously an important part of your work. And again, a nice reminder to us that we're not here on solo endeavours. We're here listening to, working with and researching with others. And lovely that you're able to do that also with Karen all the way through. So really nice. I also want to acknowledge the work you do for us at a divisional level. In administration and management. I think it's worth adding that in a vote of thanks to you on an IPL. And I'm really grateful that while your career research-wise is all about waiting for walls to fall down and measuring erosion, I'm thankful that you do the opposite in your roles as in division, and that is that you're trying to find ways to make things better and work better for our students and our staff. And so I want to acknowledge all of the work that you've done as Associate Dean Graduate Studies, and that building up that you do of us. And we will wait and see how that MA works out. Thank you, Wayne. So I get to end by congratulating you. So whakamihi kia koe, ahorangi Wayne Stephenson, Professor Wayne Stephenson. It is a title well deserved, and it's a thrill for us to be here and celebrate that with you. And I also want to say a thank you to all of you who are here with us in person and those who are online watching. It's wonderful to be able to celebrate with colleagues and friends and family, and just general members of the public who are interested. And this is what university life should be like, that we share these occasions and say well done. So congratulations and thank you to all of you. Please join us afterwards at the staff club for some food and a cup of tea and a chance to congratulate Wayne in person. And I will end with the best, well, it's not the best bit, sorry, it's the best bit of my talk, not the best bit of the evening. And that is a koha to Wayne to acknowledge this evening. So thank you.